So let's look at how we can illustrate ionic bonding with Lewis symbols. So it says draw Lewis symbols for potassium and chlorine. So potassium is K and chlorine is Cl minus. Pardon my handwriting because my Apple Pencil decided it wasn't going to participate anymore. How many valence electrons does potassium have? 1, right? It's in group 1. How many does chlorine have? 7. So 7 electrons. I have 8 places around it. I'm going to choose to put the 1 unpaired electron over there next to the potassium, really just because I'm anticipating what I'm going to do with these guys. So the octet rule says these guys are going to try to get 8 valence electrons. So it's fairly easy to see how chlorine can satisfy that. Chlorine needs to get an extra electron, right? So chlorine says, hey potassium, can I have that electron? And potassium says, okay. So we take it off there and we put it on the chlorine. Ta-da, valence. 8 valence electrons. But this has a charge now. It's not a neutral atom, and so I'm going to put brackets around it and write the charge on the outside of the brackets. You can imagine how that negative sign might get mixed up in the dots, right? So we put the brackets to contain the dots, put the charges on the outside. What about potassium? It's got a positive charge now. Does potassium have an octet of electrons? Doesn't look like it, but it does. So we can see from potassium's electron configuration what's going on. So here's potassium's electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. When it loses an electron, it's going to lose that valence electron. It's going to lose this guy right here. That one gets transferred to chlorine. So now, where are the valence electrons? Now the valence electrons are in the 3rd level. And how many are there? There are 8. So potassium had 1 extra electron on the outside that if he just got rid of that, underneath he's got this beautiful octet of electrons. Okay? Why don't we just put all the dots around there? Because it will get confusing. Where did those dots come from, right? Potassium had 1 dot and now it suddenly got 8. And so we're never going to do that in Lewis structures. You draw the atoms as they are and you can move the dots around. What happens here is that we just understand that when something loses all of its valence electrons, that underneath is a full shell. Does that make sense? So that's the Lewis symbol for potassium chloride. Let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. Well, magnesium is Mg, right? How many valence electrons? 2 in group 2, right? And then we got nitrogen. Let's make nitrogen green. How many valence electrons does nitrogen have? 5, right? So that means there's going to be 2 that are paired up and 3 that are not. Lewis symbols for magnesium and nitrogen. Okay? So these 2 things are going to form a compound, right? The goal is to get 8 valence electrons. Nitrogen is a nonmetal. It's going to gain electrons. Magnesium is a metal. It's going to lose electrons. So the nitrogen's going around begging for electrons, and he sees magnesium and says, hey, give me those extra electrons you've got. They're not really extra, but those are making you look like a dork. I'll take those off your hands. And then underneath, you've got that nice full octet of electrons. So magnesium's like, okay. So we take these 2 electrons from magnesium and we give them to nitrogen. Now, nitrogen has a 2- charge. And what's the charge on magnesium? 2+, right? Because it lost 2 electrons. Is everybody happy? Does everybody have an octet? No. Nitrogen's happier, but she's got 7 electrons now. So what do we do? Well, if there's one magnesium atom, there's probably 50 gazillion others, even if it's just a teeny tiny piece, right? So bring in another magnesium atom. Here's the second magnesium atom, also has 2 valence electrons. That nitrogen needs 1 more. So he's going to take 1 of these electrons. Now that magnesium has a +1 charge. And we'll put that electron on the nitrogen. The nitrogen now has a 3- charge. Is everybody happy? Is this magnesium happy? No. This magnesium's happy, the nitrogen's happy, this magnesium's not happy. He needs to unload 1 more electron. So who might be around that could take another electron? If there's 1 nitrogen atom, right, there's probably make up some ginormous, ridiculous number. Okay, so bring in another nitrogen atom. This nitrogen atom also has 5 valence electrons. So this magnesium can get rid of this electron by giving it to the nitrogen. We'll get rid of that. Stick it up here on this nitrogen. Now this nitrogen is going to have a charge, right? We'll have a -1 charge. And the charge on that magnesium now is 2+. Is everybody happy yet? No, not quite. Now we've got 2 magnesium ions that are good, and 1 nitrogen ion, and then we've got this nitrogen ion that's just kind of stuck in the middle. It needs 2 more electrons. Where could it possibly get 2 more electrons? Well, if you have 2 magnesium ions, there's probably another magnesium atom around there somewhere, right? Bring in another magnesium atom with its 2 valence electrons. You see how this is working? It is going to come to an end now. It doesn't go on forever. So this magnesium atom is trying to get rid of 2 electrons so it can have a full valence. So this nitrogen ion has gained 1 electron, but it needs 2 more. And so these guys can cooperate, and we can move those 2 electrons to the nitrogen. And now we have a 2+ charge on that magnesium and a 3- charge on the nitrogen. Is everybody happy? Yes.
So, again, we moved it the first time. So
Mm-hmm.
the first time you moved, I think it was you moved the 3 over.
Mm-hmm.
So it's a -3 charge for the nitrogen atom. But it's like where did you get the other? Because I think you moved some more over. So it's like,
Right. So what happened is this one had 2 electrons, and I moved 2 over to the nitrogen. But that wasn't enough. So then I brought in another magnesium with 2 electrons. 1 of those electrons went to this nitrogen. And 1 of them went to another nitrogen. And then I had to bring in a 3rd magnesium atom with 2 electrons to finish out this. Pardon me?
You're just bringing in more magnesium atoms.
Right. Yes. Because if this reaction was occurring, if you had visible amounts of magnesium and nitrogen, you would have close to Avogadro's number of atoms. So it's not like that's unrealistic. It's very realistic. There are more atoms around.
So it's kind of you just bringing in how many magnesium atoms will it take to make this amount of that?
Yeah. I'm just bringing in what's needed, because if I drew all of them, we'd have a hard time seeing it, right? And it would take me the rest of my lifetime. And yeah, I think you'd get bored and leave. Yeah. And so we're not actually going to go through this process all the time, but this helps us to understand why the formula for magnesium nitride is Mg3N2. So, after having done all of that, we say, oh, well, I have 3 magnesiums and 2 nitrogens. That's the formula for this compound. The reason it has that formula is because of what's going on with the valence electrons. Okay? We learned how to predict this formula back in chapter 3. We're in chapter 8 now. We're past that. But now we're looking at why did that happen. Any other questions? Lattice energy, the rest of the story. So when ionic compounds form, it's actually a very exothermic process most of the time. So here, if we have sodium reacting with chlorine, we're forming sodium chloride. The standard formation enthalpy for that is minus 411 kilojoules per mole. It's releasing energy. Let's look at where is that energy coming from. Well, we have an ionization energy for sodium, because sodium is becoming a +1 cation. So we have to remove 1 electron from sodium. That requires an investment of 496 kilojoules per mole, because we have to convince sodium to let go of that electron. Chlorine has a negative electron affinity, so when we give that electron to chlorine, we get a release of energy, so a return on the investment, release of energy of 349 kilojoules per mole. But if we just look at that electron affinity and ionization energy, forming those 2 ions actually requires an input of 147 kilojoules. It does not give us 411 kilojoules being released. So something's missing, right? And what's missing is electron affinity. Lattice energy. Lattice energy. So lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. And it's quantified as from gaseous ions. So if we think about this, we've got cations and anions are oppositely charged. When we bring them close together, they're attracted to each other, and their potential energy is lowered. Well, if the energy of the ions is lower, that energy has to go somewhere. It's released into the surroundings as heat. It's important to understand that the formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. I talk about atoms like that, but of course they don't actually want anything, right? And the metal actually requires an input of energy to remove that electron. But the reason that the formation of ionic compounds is exothermic is because when you bring those charged particles together, their energy is lowered, and then you get a release of a lot of heat. So here we have illustration. So sodium ions and chloride ions formed in the gas state, and they're going to be attracted to each other, and they're going to, I kind of imagine this making some sort of a noise, like whoosh, it's just all sucking in together and forming this. That lowers their energy. The energy that they're losing has to go somewhere, it goes off as heat. So it releases a lot of heat. The amount of energy that's released when this happens is the lattice energy. It's the energy of the lattice of ions. Any questions? So lattice energy is not something that's easy to measure, because it's hard to get a situation where you have a whole bunch of sodium and chloride ions in the gas state where you can actually measure it. You can't just say, okay guys, hold on. Okay, I got you all out there. Okay, go. And then measure the heat released when they swarm together, because they're just going to do that without you telling them. So how do you figure out what that lattice energy is? The easiest way is what we call a Born-Haber Cycle. It's named after two scientists. And this makes use of the idea of Hess's law, that if we can find hypothetical steps that represent the formation of this, we can add up the energy changes from those hypothetical steps and figure out what the lattice energy is. So what we're going to do is we're going to use steps for which the heat of formation is known. And then we also have to have the overall change in enthalpy. So we know the overall change in enthalpy, and then we can look at these heats of formation, and then we can find the missing piece, which is the lattice energy. So that might look something like this. So this needs a little explaining. So we're looking at the formation of sodium chloride. So here we have sodium and chlorine in their normal element states, and they're going to react and they're going to form sodium chloride. This heat of formation, this is a heat of formation which is known because we're taking elements in their standard states and making 1 mole of compound. So we could look that up. To find the lattice energy, what we're going to do is we're going to imagine forming the ions. So we're going to take sodium in the solid state and put it into the gas state. That's going to require us to put in energy. That's step 1. And then we're going to take this diatomic chlorine and we're going to separate that into atoms. That also requires energy to be put in. That's step 2. And then we're going to make the sodium into an ion. That requires more energy. This is not how it happens, but we can imagine these individual steps that the energy change is known. So we're just imagining this happening. And then the last thing that has to happen is we have to take that chlorine and make it into an ion. This is a decrease in energy because the electron affinity for chlorine is negative. So it releases energy when you give it that electron. So that's step 4. So we know all of these steps and we know this overall change. So we can calculate this change going from sodium and chloride ions in the gas state to sodium chloride as a solid. This big energy change here is the lattice energy. Does that make sense? We can't measure this directly, so we measure around it and figure it out by difference. So there are trends in lattice energies, and one of those is ion size. So if we look at the metal chlorides, lithium, sodium, potassium, and cesium chloride, so the anion here is the same. The metals here are all alkali metals. And we can look at the lattice energy, which other people have figured out. Minus 834, minus 788, minus 701, minus 657. So the lattice energy is getting smaller. We're going down a group here. Why is the lattice energy getting smaller? We're releasing less energy when that solid forms. It's because of the sizes of the atoms or the ions. So the chloride ion is the same size, right? The lithium, the metal ions are of different sizes, and as we go down the periodic table, the ion sizes increase. So cesium is larger than lithium. The size of the ions is going to determine the distance between the nuclei, the bond length. So here it's 241 picometers, down here it's 348 picometers. Well, Coulomb's law tells us that the energy is proportional to 1 over R. The larger the distance between the two things, the less attracted they are. The shorter the distance, the more attracted they are. So lithium chloride has a larger lattice energy, a more negative energy. It's going to release more energy because the lithium ion is smaller, and these two charged particles can get closer together. Does that make sense? Ion charge also has an effect. This effect is even bigger. If we look at sodium fluoride and calcium oxide. So the bond length here, the sum of the radii, 231 and 239. Pretty close, right? And yet, calcium oxide has a lattice energy of minus 3,414 compared to minus 910. Much, much bigger. It's because of difference in charges. Lithium and fluoride, +1 and -1. Calcium and oxygen, +2 and -2. Coulomb's law tells us that the energy is proportional to the product of the charges. So for sodium and fluoride, where we have +1 and -1, that multiplied is going to equal -1. And over here, we've got +2 and -2, and that's going to equal -4. So based on the charges, we would expect that this one has a lattice energy that's 4 times that of this one. Well, what's 4 times 900? 3,600. It's pretty close. Does that make sense? Higher charges, more attraction. Larger lattice energy, stronger bond. So lattice energies become less exothermic with increasing ionic radius. You're going to release less energy as the atoms get bigger because they can't get as close together. Lattice energy is going to become more exothermic. They're going to release more energy as the charges get larger. So these sorts of problems kind of end up being a little bit like a logic problem on the SAT. Arrange the following in order of increasing magnitude of lattice energy. So again, in order of increasing means that you start with the small and you go to the big. So we've got lithium bromide, potassium ion, and calcium oxide. And we have to compare these 3 things. Well, you can't compare 3 things at once. You can only compare 2 at a time. So let's start with the first 2. So lithium bromides, we have Li plus and Br minus, and we have K plus and I minus. So the 2 things that we're looking at here are charges and ion size. Comparing these 2 compounds, the charges are the same, right? They're both +1, -1. So that's not going to have an effect. So any differences must be due to ion size. So if we compare lithium ion with potassium ion, which one's bigger? Potassium's bigger, right? So this one's bigger, and this one's smaller. And then let's look at the anions. We've got bromide and iodide. Of those 2, which one's bigger? Iodide. So this is bigger, and this one's smaller. So we've got 2 small ions compared to 2 big ions being attracted to each other. Which pair can get closer together? The small ones, right? These guys can get closer together. The attraction between them is larger. Their lattice energy is larger. So lithium bromide is not first in this list. Lithium bromide has a higher, larger, more negative lattice energy than potassium iodide. Comparing ion sizes. Lithium ion is smaller than potassium ion. And bromide ion is smaller than iodide ion.
So you're comparing them up and down, next to each other? Like you're comparing the lithium with the potassium?
Yeah, I'm comparing the sizes of the two cations to each other and the two anions to each other because comparing lithium to bromide is not going to give me any information. Yeah. Any other questions? So now we need to look at the calcium oxide. So calcium oxide is Ca2 plus and O2 minus. So the charges there are larger. A bigger charge difference like that is going to have a bigger effect on the lattice energy than the sizes of the atoms. But let's look at where these ions are in size. There's calcium, and here's oxygen. So calcium, the calcium ion is probably bigger than the lithium ion. Is it larger or smaller than the potassium ion? What's the trend in atomic size as we go across?
Smaller.
Gets smaller. So the atoms were smaller, and then when they become ions, they become even smaller. So calcium here is probably a little smaller than potassium. And then we look at oxygen. Is oxygen larger or smaller than these two? Smaller. So oxygen's smaller than either of those, and calcium's kind of in the middle, but here we have +2 and -2. And so the charge effect, this would be a -1, a -1, and a -4. So does calcium oxide have a larger lattice energy or a smaller lattice energy? Larger, right? So we're going to put calcium oxide over here. So if you think of magnets on the refrigerator, these are two of those like really, really strong magnets, right? They're going to go boom, they're just stick really hard. And these are just like regular magnets, and they stick, but not so great. And here, when you have a small distance, that's like one piece of paper between them, and a large distance, you've got several pieces of paper. And that magnet's just like barely hanging on, and it might even start sliding down, right? Because when you separate the charges, the attraction decreases. Here we have small distance between them and really high charges. And so this is going to have the highest attraction, the largest lattice energy. Yeah.
Where'd you get the -4 from?
I got the -4 because the energy is proportional to Q1, Q2, which is the charge of this one and the charge of that one. +2 times -2 is -4. And this is +1 and -1 multiplied is -1. Any questions? So you should be able to do a problem like this. Then we have to ask ourselves, does our model match up with reality? Well, we observe that ionic compounds have high melting points, and that the solid form of them is non-conductive, but that the solution form does conduct electricity. When we have a solid ionic compound like solid sodium chloride, the ions are fixed in place. They can't move. If we take that solid and dissolve it in water, we separate the ions. The ions are now able to move through the water. The light bulb goes on. Electricity is conducted. It will not conduct through solid sodium chloride because charge cannot flow. There's nothing to carry the charges. If you melt sodium chloride, if you form a liquid, that doesn't happen in our everyday lives, but you can melt sodium chloride. Now the ions can move, and molten sodium chloride does conduct electricity. The high melting point that we observe for ionic compounds fits with this model because what we have is non-directional bonds. Any given ion is attracted in all four directions, all six directions to other ions. And so we don't have just a single bond that could be broken, we have bonds extending in all directions, and so it takes a lot of energy to melt that.